Tonight, we're going to explore something you feel every single day, but almost certainly misunderstand. Heat. You feel it when you touch a hot cup of coffee. You feel it radiating from the sun on your skin. It seems so obvious, so simple. Hot things have heat. Cold things don't. But here's what most people never learn. For over a century, the greatest scientists in the world believed heat was an invisible fluid flowing between objects. They were completely wrong. Heat isn't a substance at all. It's not something inside matter. It's not something you can trap in a bottle. When you dig into what heat actually is at the quantum level, when you look at the vibrating, colliding, quantum jumping particles that make up everything around you, the answer turns out to be far stranger and far more beautiful than anyone expected. And it changes how you understand reality itself. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something everybody knows. You put your hand on a hot stove and it burns. You hold a mug of coffee and warmth seeps into your fingers. You stand in front of a campfire and you feel heat pressing against your face, even though you're not touching the flames. You step outside on a summer day and the sun's warmth soaks into your skin. You step back inside an air-conditioned room and coolness washes over you. These experiences are universal. Every human being who has ever lived has felt heat. It's one of the most basic, most immediate sensations we possess. We feel it before we can walk, before we can talk, before we understand the first thing about what it means. And because heat is so familiar, most people assume they understand it. The intuitive picture seems obvious. Hot things are full of some kind of heat stuff. Cold things have less of it. When something hot touches something cold, the heat stuff flows from the hot object to the cold one, like water pouring from a full glass into an empty one. The flow continues until both objects reach the same temperature, the same level, and then it stops. Simple, intuitive, case closed. But here's the problem. That intuitive picture, the one that feels so natural and so self-evident, is fundamentally wrong. Not partially wrong, not slightly off. Completely, deeply, structurally wrong. And the story of how science discovered this, how humanity went from thinking heat was a substance to understanding what it actually is, represents one of the most important revolutions in the entire history of physics, because it leads directly to the atomic theory of matter, to the laws of thermodynamics, and ultimately to quantum mechanics itself. All of that from asking a deceptively simple question: what is heat? To understand why heat fooled scientists for so long, you have to appreciate just how naturally the wrong answer fits what we observe. If you put a hot iron bar into a bucket of cold water, the bar cools down and the water warms up. Something clearly moved from the bar to the water. You can feel it happening if you put your hand near the bucket. The water gets warmer, the bar gets cooler. Whatever heat is, it seems to flow like a liquid, moving from regions of high concentration to regions of low concentration, settling out like water finding its level. That's how it looks. That's how it feels. And that's exactly how even careful, rigorous scientists interpreted it for generations. This observation, the simple, everyday experience of hot things cooling down and cold things warming up, was the foundation for what became one of the most widely accepted scientific theories in history. It was called the caloric theory. And for well over a century, from roughly the 1760s through the 1850s, nearly every serious scientist in the world believed it. The caloric theory stated that heat was a real physical substance, an invisible, weightless, self-repelling fluid called caloric. Every object contained a certain amount of this fluid. Hot objects had lots of caloric, cold objects had less. When a hot object touched a cold one, caloric flowed from the hot object into the cold one, exactly like water flowing downhill from a high point to a low point. The flow continued until both objects held the same concentration of caloric, at which point they were at the same temperature and the flow stopped. Caloric was conserved. It could not be created or destroyed, only moved from place to place. And it was self-repelling, meaning it naturally spread itself out as evenly as possible, which explained why temperature differences always tend to equalize over time. This wasn't some casual guess or idle speculation. It was a fully developed scientific framework endorsed by the most respected names in science. The great French chemist Antoine Lavoisier, one of the founders of modern chemistry, included caloric on his official list of chemical elements, published in 1789. He treated it as a genuine substance, as fundamental and as real as oxygen or hydrogen or carbon. The Scottish scientist Joseph Black, working carefully in the 1760s and 1770s, developed the foundational concepts of specific heat and latent heat entirely within the caloric framework. His measurements were meticulous, his reasoning was rigorous, and his results seemed to confirm that caloric was exactly what it claimed to be: a real physical substance with measurable, predictable, reproducible properties. And to be fair, the caloric theory worked remarkably well for a wide range of everyday situations. It explained why hot objects cool down when placed in cold surroundings. Caloric flows out of them into the environment. It explained why metals feel cold to your touch compared to wood at the same temperature. Metals conduct caloric more efficiently, so they draw the fluid out of your warm skin faster, creating a stronger sensation of cold. It explained why different materials heat up at different rates when given the same amount of energy. Different materials have different capacities for holding caloric, just as different sponges absorb different amounts of water. It even explained aspects of thermal expansion. When caloric flows into an object, the fluid takes up space between the atoms, causing the object to expand slightly. If you didn't look too closely, if you stayed at the macroscopic level of beakers and thermometers, caloric theory was convincing, consistent, and genuinely useful for solving practical problems. But there was a crack in the theory, a subtle but persistent problem that a few careful observers noticed, and that would eventually bring the entire framework crashing down. That problem was friction. In 1798, an American-born scientist named Benjamin Thompson, who had been granted the title Count Rumford by the ruler of Bavaria, was overseeing the boring of brass cannons at the military arsenal in Munich. Boring a cannon means drilling out the interior of a solid brass cylinder to create the barrel. It's a slow, grinding process. A large boring tool, driven by horses walking in circles, presses against the inside of the brass cylinder and slowly grinds away the metal, shaving it into fine chips. And this process produces an enormous amount of heat. The metal gets incredibly hot. Workers at arsenals had known this for years. Machinists considered it an unremarkable nuisance, just a byproduct of working with metal. Under caloric theory, the explanation was straightforward. The boring process was grinding the brass into fine chips, breaking apart its crystalline structure, and releasing the caloric that had been locked inside. The caloric that was previously trapped within the dense solid brass was now liberated, flowing out and heating up the surrounding material. Simple enough, just like squeezing water out of a sponge. But Rumford noticed something peculiar, something that nagged at him. He noticed that the heat production seemed inexhaustible. As long as the horses kept turning the boring tool, as long as friction continued between the tool and the brass, heat kept being produced. hour after hour. It didn't diminish over time. It didn't taper off. It didn't run out. The supply of heat appeared to be absolutely limitless, completely without end, as long as mechanical work was being continuously applied from outside. Rumford designed a deliberate experiment to test the implications. He used a purposely blunt boring tool, one so dull that it barely cut the metal at all. It produced almost no brass shavings. If caloric theory were correct, then almost no caloric should be released, because the metal's structure was barely being disrupted. But the blunt tool still generated enormous quantities of heat. Rumford immersed the entire apparatus in a large vessel of water and found that the friction between the blunt tool and the brass was enough to bring the water from room temperature to a vigorous, rolling boil. And the boiling continued for as long as the horses kept turning the mechanism. The heat kept pouring out with no sign whatsoever of depletion. This was devastating to the caloric theory. If heat were a stored fluid, there should be a finite amount of it inside the brass cylinder. At some point, you should exhaust it. The metal should simply run out of caloric, just as a sponge eventually runs out of water if you keep squeezing. But that's not what Rumford observed. The heat never stopped. It kept pouring out of the brass indefinitely with no diminishment. The only thing being continuously supplied was mechanical work, the effort of the horses walking endlessly in circles. Rumford concluded that heat could not possibly be a material substance. Instead, he proposed that heat must be related to motion itself. The friction between the tool and the brass was somehow converting mechanical motion into heat. Rumford published his findings, and they were dramatic, but they didn't immediately overthrow caloric theory. Science rarely works that way. The caloric framework had decades of experimental success behind it. It had the support of the most respected chemists and physicists across Europe. Rumford's observations were suggestive, even compelling, but they weren't quite enough to convince everyone to abandon a theory that had served them well for so long. Supporters of caloric argued that perhaps the boring process was somehow altering the brass's capacity to hold caloric. Perhaps finely ground metal has different thermal properties than solid brass. Perhaps the caloric wasn't being created, just redistributed in unfamiliar ways. There were patches available, at least temporarily. The person who finally delivered the fatal blow to caloric theory was a brewer from Manchester, England. His name was James Prescott Joule. He was not a university professor. He was not a member of the scientific establishment. He was a businessman who ran his family's brewery, and he conducted experiments in his spare time with an obsessive, almost compulsive precision. His work in the 1840s represents some of the most important experimental physics ever conducted by anyone. Joule was driven by a single, relentless question. Is there a precise, fixed, universal relationship between mechanical work and heat? If heat is truly just motion appearing in another form, then a specific amount of work should always produce a specific amount of heat, regardless of how that work is performed. Whether you rub your hands together, drill into metal, churn water with paddles, or push electrical current through a wire, the conversion ratio should always come out identical. If heat is a substance, there's no particular reason such a universal relationship should exist. But if heat is energy, the relationship must exist, because energy is conserved. So Joule set about measuring it with extraordinary, almost superhuman care. His most famous experiment used a deceptively simple apparatus. He attached a falling weight to a rope wound around an axle connected to a set of brass paddles inside a carefully insulated container of water. As the weight fell under gravity, it turned the paddles, churning the water. The churning created friction between the paddles and the liquid, and the friction warmed the water by a tiny amount. Joule measured the exact distance the weight fell and calculated the mechanical work done by gravity. Then he measured the temperature rise in the water with custom-built thermometers sensitive to tiny fractions of a degree, instruments far more precise than anything commercially available at the time. The result was extraordinary. The ratio of work to heat was constant, every single time. Regardless of how fast the paddles turned, regardless of how much water he used, regardless of how many times he repeated the experiment over weeks and months and years, the same amount of mechanical work always produced the same amount of heat. Joule determined that roughly 4,186 joules of mechanical energy always raised 1 kilogram of water by exactly 1 degree Celsius. This number, the mechanical equivalent of heat, was not an approximation or a rough estimate. It was a universal constant of nature, a fixed exchange rate between mechanical work and thermal energy. And Joule didn't stop with paddle wheels. He was relentless, driven, almost possessed by the need to verify his result through every method he could imagine. He measured the heat produced by electrical currents flowing through resistors. He measured the heat generated by compressing gases rapidly. He measured the heat produced by forcing water through narrow tubes. In every case, in every configuration, using every method he could devise, he found the same relationship. Mechanical work, electrical energy, compression, friction. It didn't matter what form the energy took or how the conversion was carried out. When converted to heat, the ratio was always the same. This was the death blow for caloric theory. If heat were a material substance, there would be no fundamental reason for such a precise and universal relationship between work and heat. The ratio would depend on the substance, on the conditions, on all sorts of variable factors. But if heat is a form of energy, if it's the same fundamental quantity as mechanical work, simply manifesting in a different guise, then of course the conversion ratio is constant. Energy is conserved. It changes form freely, from motion to heat to electricity and back again. But it never appears from nothing and never vanishes into nothing. Work becomes heat. Heat can become work. They're the same thing, measured in different ways, related by an unbreakable constant of nature. By the 1850s, the scientific community had largely accepted this revolutionary new understanding. Heat is not a substance. It is not a fluid. It is a form of energy. And more precisely than that, heat is energy in transit. It's energy being transferred from one system to another because of a temperature difference between them. This distinction is crucial, and it's worth emphasizing carefully because it's something that many people, even well-educated people, still get wrong today. Heat is not something an object contains. An object contains internal energy. It has energy stored in the motions and interactions and configurations of its atoms and molecules. But that stored energy is not called heat. Heat is the name we give to energy only when it's in the process of moving between systems. Only when it's flowing from a hotter body to a cooler one, because their temperatures differ. Once the energy has been absorbed by the receiving object and is sitting inside it, contributing to its internal energy, it is no longer heat. It's simply energy stored within the object. Think of it this way. Rain is not something a cloud contains. A cloud contains water in the form of tiny suspended droplets and ice crystals. Rain is what we call that water when it's falling, when it's in transit between the cloud and the ground. Once the water lands in a puddle, it's not rain anymore, it's just water sitting in a puddle. The word rain describes a process of transfer, not a substance stored somewhere waiting to be used. Heat works exactly the same way. It describes the process of energy transfer driven by temperature differences, not a substance sitting inside objects. An object can have lots of internal energy, but it doesn't contain heat. Heat only exists as a flow. This also means that heat and temperature are not the same thing, even though people routinely use the words interchangeably in everyday conversation. Temperature tells you about the average kinetic energy of the particles inside a substance. It's a property of the object itself, something you can measure at any given moment with a thermometer. Heat, on the other hand, is the energy that flows between objects specifically because their temperatures differ. They're related concepts, but they're not identical. You can have significant heat flow with a small temperature difference if the objects involved are large, and you can have a huge temperature difference that produces very little total heat transfer if the objects are tiny. Consider a concrete example. If a tiny spark from a fire lands on the back of your hand, that spark might be at a temperature of several hundred degrees Celsius. It's enormously hot, but it carries almost no total energy because it's so incredibly small, just a minuscule fragment of glowing material with very little mass. It stings for a brief moment, but it doesn't seriously burn you because the total energy transferred to your skin is negligible. Now imagine lowering your entire body into a bathtub filled with water that's only slightly above your normal body temperature, say 40 degrees Celsius instead of your body's 37. The temperature difference is small, only 3 degrees. But the bath contains an enormous quantity of thermal energy because there's so much water surrounding you. The total energy your body absorbs from the bath over time is far greater than from that tiny spark, even though the spark was hundreds of degrees hotter. The spark has high temperature but transfers little energy. The bath has a small temperature difference but transfers a great deal. Temperature and heat are related, but they measure fundamentally different things. Understanding this distinction is essential to grasping what heat really is. So, if heat is energy being transferred, the next question is immediate and unavoidable. What carries it? What is actually happening at the microscopic level when energy moves from a hot object to a cold one? What does this transfer look like if you could somehow zoom in and watch individual atoms doing their work? This is where the kinetic theory of matter enters the story, and it's where things start to become truly fascinating. The idea that matter is made of tiny particles in constant motion has surprisingly ancient roots. Greek philosophers like Democritus proposed over 2,000 years ago that everything was composed of indivisible particles called atoms. But it was a philosophical speculation, not a testable scientific theory. It took until the 1800s for science to develop this idea into a rigorous, mathematical, experimentally verified framework for understanding heat. The basic concept is this: everything around you, every solid, every liquid, every gas, is made of atoms and molecules. And those atoms and molecules are never sitting perfectly still. They are always in motion. In a gas, molecules fly freely through open space, traveling in straight lines at speeds of hundreds of meters per second until they collide with another molecule or with the walls of their container. These collisions happen billions of times every second. In a liquid, molecules are closer together, still moving freely but constantly jostling and bumping against their neighbors in a crowded, chaotic, swirling dance. In a solid, atoms are locked into fixed positions within a crystalline lattice, bonded to their neighbors in an orderly grid. But even there, they're not motionless. They vibrate rapidly back and forth around those fixed positions, oscillating like tiny springs connected to all their neighbors, buzzing with energy they can never fully shed. This incessant microscopic motion is what we experience as thermal energy. The faster the particles move on average, the higher the temperature. The slower they move, the lower the temperature. When you heat a pot of water on a stove, you're not adding any substance to the water. You're making its molecules move faster. The flame transfers energy to the metal of the pot, causing the metal atoms to vibrate more vigorously in their lattice. Those vibrating metal atoms nudge the water molecules they're in contact with at the inner surface of the pot, transferring kinetic energy to them and speeding them up. The water gets hotter because its molecules are now moving more quickly, colliding more forcefully, carrying more kinetic energy on average. Nothing was poured in, nothing material was added or removed. the molecules simply started moving faster. Daniel Bernoulli proposed an early version of this kinetic picture as far back as 1738, suggesting that gas pressure resulted from the motion of countless tiny particles constantly colliding with the walls of their container. More particles moving faster meant more forceful collisions per second, which meant higher pressure. It was an elegant and prescient idea, but it was largely ignored for over a century because caloric theory was so deeply entrenched in the scientific establishment. It wasn't until the work of Rudolf Clausius in the 1850s and Ludwig Boltzmann in the 1860s and 1870s that the kinetic theory of gases was developed into a rigorous mathematical framework that could make precise, testable predictions. These scientists worked out the detailed mathematics of how molecular speed distributions relate to temperature, how collisions transfer energy between molecules of different speeds, and how the macroscopic properties of gases like pressure, volume, and temperature emerge naturally from the collective behavior of enormous numbers of individual particles. Boltzmann's contribution was particularly profound and far-reaching. He demonstrated that temperature is not a property of individual particles. A single molecule doesn't have a temperature. Temperature is a statistical property, a quantity that only makes sense when you're talking about vast collections of particles, trillions upon trillions of them, each moving at its own speed in its own direction. Some molecules in any given sample are racing along at high speeds. Others are barely crawling. Most are somewhere in between. The temperature of the substance corresponds to the average kinetic energy across all those particles. It's the statistical mean of an enormous distribution. Your thermometer doesn't measure any individual molecule's velocity. It measures the collective, averaged-out effect of all of them together. This statistical view also reveals something remarkable about the second law of thermodynamics, the law that says energy spontaneously flows from hot objects to cold ones, never the other way around. This isn't because there's some cosmic force physically pushing energy in one direction. There's no invisible hand compelling heat to flow from hot to cold. Instead, it's purely about probability. Overwhelming, staggering, astronomically lopsided probability. When a fast-moving molecule from a hot region collides with a slow-moving molecule from a cold region, there are enormously more possible outcomes where the fast molecule surrenders some of its kinetic energy to the slow one than outcomes where the slow molecule somehow gives energy to the fast one. It's not impossible for energy to flow from cold to hot in a single collision. That can happen by chance. But when you have trillions upon trillions of particles all colliding simultaneously, the probability that the net flow of energy goes from cold to hot is so vanishingly, incomprehensibly small that it effectively never happens in practice. The second law of thermodynamics isn't a fundamental commandment written into the deepest structure of reality. It's a statistical certainty, an inevitable consequence of probability applied to unimaginably large numbers of randomly interacting particles. And this brings us to the crucial insight about what heat truly is at the microscopic level. When energy transfers from a hot object to a cold one, what's actually happening is that faster-moving particles in the hot object are colliding with slower-moving particles in the cold object and sharing some of their kinetic energy through those collisions. That's it. There's no fluid, there's no substance flowing, there's nothing material traveling from one object to the other. There are just particles bumping into each other, exchanging momentum and kinetic energy through contact. And the net statistical result of trillions upon trillions of these collisions per second is that energy migrates from the region where particles move faster on average to the region where they move slower on average. When you wrap your hand around a hot ceramic mug and feel warmth spreading slowly into your fingers, here is what's actually happening at the atomic scale. The atoms on the surface of the ceramic are vibrating rapidly because the mug is hot. When your skin presses against the mug, those fast vibrating ceramic atoms collide with the slower moving molecules in the outer layers of your skin. Each individual collision transfers a tiny, almost negligible amount of kinetic energy from a mug atom to a skin molecule. But billions upon billions of these microscopic collisions are happening every fraction of a second across the entire area where your fingers meet the ceramic. The cumulative effect of all those collisions is that your skin molecules start vibrating faster, which your sensory nerve endings detect as a rise in local temperature and interpret as the familiar sensation of warmth. No substance moved from the mug to your hand. No fluid flowed between them. Energy moved, carried by nothing more exotic than the accumulated mechanical effect of countless microscopic collisions between vibrating particles at a surface. This is a beautiful and elegant picture, and it's largely correct, but it is also incomplete. The kinetic theory of heat, as powerful and successful as it is, cannot explain everything about thermal energy. It cannot explain why the heat capacity of solid materials drops dramatically at very low temperatures, a behavior that classical physics based on smooth, continuous energy predicts should never happen. It cannot explain why hot objects glow with a very specific spectrum of light that follows precise mathematical rules that classical theory gets catastrophically wrong. And it cannot explain why energy appears to come in specific, discrete amounts, rather than in any arbitrary quantity. These puzzles, these stubborn failures of the classical kinetic picture, demanded something entirely new. They demanded a revolution in how we understand energy at its most fundamental level. They demanded quantum mechanics. And it's in the quantum world that the story of heat becomes truly extraordinary. Because at the quantum level, heat is not simply particles bumping into each other and sharing speed. It's particles jumping between specific, discrete, allowed energy states. It's vibrations that come in indivisible packets that cannot be broken apart. It's photons carrying energy silently across the vacuum of empty space. The microscopic world of thermal energy is far richer, far more structured, and far more surprising than even the brilliant architects of kinetic theory could have imagined. We now understand that heat is not a substance. It's energy being transferred between systems because their temperatures differ. And we know the broad picture. Atoms and molecules are in constant motion, and the energy of that motion is what we experience as thermal energy. But this broad picture, while correct, is far too simple. It glosses over a rich, intricate world of microscopic mechanics that determines everything about how materials store energy, how they share it, and why different substances behave so differently when you heat them up or cool them down. To truly understand what heat is made of at the physical level, you need to look much more carefully at what atoms and molecules actually do with the energy they carry. Because here's something most people never consider. When you add energy to a substance, that energy doesn't just make the particles move faster in a straight line. The energy gets distributed across multiple different types of motion simultaneously. And the particular ways a molecule can move, the specific channels through which it can absorb and store energy, determine everything about how that substance responds to heat. This concept is so important in physics that it has a formal name: degrees of freedom. And understanding degrees of freedom is essential to understanding thermal energy at the microscopic level. Let's start with a gas, because gases are the simplest case. The molecules in a gas are flying freely through open space, bouncing off each other and off the walls of whatever container holds them. Consider a single atom of a simple noble gas, like helium or argon. A lone atom like this is essentially a tiny sphere. It has no internal structure you need to worry about at everyday temperatures. The only thing it can do with energy is move through space. It can move in 3 independent directions: left and right, forward and backward, up and down. Each of these directions of motion represents 1 degree of freedom. So a single atom in a gas has 3 translational degrees of freedom. It can carry kinetic energy by flying in any combination of those 3 directions. The faster it moves, the more kinetic energy it carries. Now consider a molecule made of 2 atoms bonded together. Oxygen in the air you're breathing right now exists as O2, two oxygen atoms joined by a chemical bond. This molecule can do everything a single atom can. It can fly through space in 3 dimensions, giving it the same 3 translational degrees of freedom. But it can also do something a single atom cannot. It can rotate. Picture the O2 molecule as a tiny dumbbell, 2 balls connected by a rod. That dumbbell can spin around 2 independent axes, perpendicular to the line connecting the 2 atoms. Each axis of rotation is an additional degree of freedom. The molecule can store kinetic energy by tumbling end over end around either axis. So now we have 5 degrees of freedom, 3 translational and 2 rotational. The molecule has more ways to absorb and carry energy than a single atom does. But there's more. The 2 atoms in the molecule are connected by a chemical bond, and that bond behaves like a tiny spring. The atoms can vibrate toward and away from each other, stretching and compressing the bond. This vibrational motion adds yet another way for the molecule to carry energy. Actually, it adds 2 degrees of freedom, because the vibration involves both kinetic energy as the atoms move back and forth, and potential energy stored in the stretched or compressed bond. So in principle, a diatomic molecule like O2 or N2 has 7 degrees of freedom in total, 3 translational, 2 rotational, and 2 vibrational. For a molecule with 3 or more atoms, the situation becomes even more complex. A water molecule, H2O, is bent into a V shape. It has 3 translational degrees of freedom, 3 rotational degrees of freedom because it can rotate around 3 independent axes since it's not a linear molecule, and multiple vibrational modes. Each vibrational mode involves the atoms oscillating in a specific pattern. One mode might involve the 2 hydrogen atoms stretching away from the oxygen simultaneously. Another might involve them pinching together. Another might involve the angle between the bonds changing, while the bond lengths stay the same. A water molecule has 3 distinct vibrational modes, each contributing 2 degrees of freedom. That gives water molecules a total of 12 degrees of freedom, 3 translational, 3 rotational, and 6 vibrational. A molecule of carbon dioxide, CO2, which is linear, has its own distinct set of modes. Each molecule has its own unique set of vibrational patterns, determined by its geometry, its bond strengths, and the masses of its constituent atoms. Why does all this matter for heat? Because of a principle that lies at the heart of classical thermal physics. It's called the equipartition theorem, and it was developed through the work of James Clerk Maxwell and Ludwig Boltzmann in the 1860s and 1870s. The equipartition theorem states something beautifully simple. At thermal equilibrium, energy distributes itself equally among all available degrees of freedom. Each degree of freedom gets the same average share of the total thermal energy. If a molecule has more degrees of freedom, it can absorb and store more energy per molecule for a given temperature than a molecule with fewer degrees of freedom. This is a profound result. It means the microscopic geometry of a molecule, its shape, its bond structure, the number of atoms it contains, directly determines how much energy is needed to raise its temperature by a given amount. In other words, the molecular architecture of a substance determines its specific heat capacity, the amount of energy required to raise a unit mass of that substance by 1 degree. Consider the simplest comparison. A monatomic gas like helium has 3 degrees of freedom per atom. A diatomic gas like nitrogen has 5 active degrees of freedom at room temperature, 3 translational plus 2 rotational. The vibrational modes of nitrogen are effectively frozen out at room temperature, a puzzle we'll return to shortly because it's crucial. Since nitrogen molecules have more active degrees of freedom than helium atoms, it takes more energy to raise the temperature of nitrogen by 1 degree. Each nitrogen molecule has to distribute the incoming energy across 5 channels instead of 3. More channels means more energy absorbed before the average energy per channel, which is what temperature measures, increases by the same amount. This prediction from the equipartition theorem matches experimental measurements beautifully. The specific heat capacity of diatomic gases is measurably and predictably higher than that of monatomic gases, exactly as the theorem demands. Now let's turn to solids, because energy storage in solid materials is a completely different world from the free-flying molecules of a gas. In a solid, atoms are not roaming freely through space. They're locked into a rigid lattice, a three-dimensional grid of fixed positions held in place by strong bonds to all their neighbouring atoms. Each atom sits in a potential well created by the combined attractive and repulsive forces of every atom surrounding it. The atom can't translate freely through the material the way a gas molecule flies through its container. It can't rotate in any meaningful sense because it's bonded firmly to its neighbours on all sides. The only thing it can do is vibrate. Each atom in a solid vibrates around its equilibrium position in 3 dimensions. It oscillates back and forth along 3 independent directions within the lattice. Each direction of vibration contributes 2 degrees of freedom, one for the kinetic energy of the vibrating motion, and one for the potential energy stored in the displaced bonds. So each atom in a solid has 6 degrees of freedom, all vibrational. 3 for kinetic energy and 3 for potential energy. This leads to an important prediction about solid materials. In 1819, 2 French physicists, Pierre-Louis Dulong and Alexis-Thérèse Petit, observed experimentally that many solid elements have roughly the same heat capacity per atom, regardless of what element they are. Gold, copper, iron, aluminium, lead, it didn't matter. When measured per mole of atoms, the specific heat came out to nearly the same value every time, approximately 25 joules per mole per degree Celsius. This observation, known as the Dulong and Petit law, was a mystery when first discovered. Why should such wildly different materials all require the same amount of energy per atom to raise their temperature? The equipartition theorem provides the explanation. If every atom in a solid has 6 degrees of freedom, and each degree of freedom carries the same average energy at a given temperature, then every solid element should store the same amount of thermal energy per atom at the same temperature. It doesn't matter whether the atoms are heavy or light, whether the bonds are strong or weak, whether the material is soft like lead or hard like diamond. The energy per atom depends only on the number of degrees of freedom and the temperature, not on the specific identity of the atom. The Dulong and Petit law falls naturally out of the equipartition theorem. It's not a coincidence. It's a direct consequence of how energy distributes across microscopic degrees of freedom. But here is the critical point. The Dulong and Petit law works well at room temperature and above, but at low temperatures, it fails. As you cool a solid toward absolute zero, its heat capacity doesn't stay constant. It drops, and it drops dramatically. Diamond, for instance, has a heat capacity far below the Dulong and Petit prediction at room temperature, and it falls even further as the temperature decreases. At very low temperatures, the heat capacity of every solid approaches zero. Classical physics, the equipartition theorem included, has absolutely no way to explain this. According to classical theory, each degree of freedom should always carry its fair share of energy, regardless of temperature. The heat capacity should be constant. The fact that it's not, the fact that degrees of freedom seem to shut off one by one as the temperature drops, was one of the great unsolved puzzles of classical physics. And it would take a revolution in our understanding of energy itself to explain it. But we'll come to that revolution in due course. For now, let's follow the energy as it moves through a solid material. Because the way thermal energy travels through a solid tells you something fundamental about what heat transfer actually looks like at the atomic scale. When you place one end of a metal rod into a flame, the other end gradually warms up. energy somehow moves through the rod from the hot end to the cold end. This process is called thermal conduction, and at the atomic level, it works through a remarkably simple mechanism. The atoms at the hot end of the rod are vibrating violently. They've absorbed energy from the flame and are oscillating with large amplitudes around their lattice positions. These energetically vibrating atoms are bonded to their neighbors, and through those bonds, they tug and push on the atoms next to them. Think of it as a long line of people standing shoulder to shoulder. If the person at one end starts swaying back and forth, their motion pushes and pulls on the person next to them, who starts swaying too, which pushes on the next person, and so on down the line. The disturbance propagates through the line without any person actually moving from their position. Each person stays in place, but passes the energy of the motion along to their neighbor. That's essentially how conduction works in a solid lattice. Vibrating atoms at the hot end nudge their cooler neighbors, transferring kinetic energy to them through the bonds. Those newly energized atoms then nudge their even cooler neighbors on the far side, passing energy further along. Step by step, collision by collision, atom by atom, energy ripples through the material from the hot region to the cold region. No atom moves from one end of the rod to the other. No material flows. The atoms stay fixed in their lattice positions the entire time. Only the energy moves, hopping from one vibrating atom to the next through the mechanical coupling of chemical bonds. This is heat conduction in its purest form. Energy transfer through a chain of microscopic vibrations. And the speed and efficiency of this transfer depend on the properties of the lattice. Materials with stiff, strong bonds transmit vibrations more effectively because each atom's motion is more forcefully communicated to its neighbors. Materials with regular, orderly crystal structures transmit vibrations better than disordered or amorphous materials because the orderly arrangement allows vibrations to propagate coherently. Diamond, for instance, has extremely stiff carbon-carbon bonds arranged in a perfectly regular crystal lattice, and it's one of the best thermal conductors known, despite being an electrical insulator. But in metals, there's an additional mechanism at work that makes them exceptionally good thermal conductors. Metals contain free electrons that are not bound to any particular atom, but instead roam freely throughout the entire metallic lattice, like a gas of charged particles flowing between the fixed positive ions. These free electrons are the same electrons responsible for electrical conductivity. They're the reason metals conduct electricity so well. These free electrons also carry thermal energy. Because they move so quickly and travel so far between collisions, free electrons can transport energy through a metal far more efficiently than lattice vibrations alone. When one end of a copper rod is heated, the free electrons near the hot end absorb kinetic energy from the violently vibrating atoms there. Those energetic electrons then race through the lattice at enormous speeds, traveling hundreds of atomic spacings before colliding with a lattice atom or another electron and depositing some of their excess energy. In this way, energy leapfrogs through the metal, carried by electrons that cover large distances between interactions, rather than being passed laboriously from one vibrating atom to its immediate neighbor. This is why metals feel cold to the touch compared to wood or fabric at the same temperature. When you touch a metal doorknob at room temperature, the metal is the same temperature as the surrounding air and the wooden door frame next to it. They're all in thermal equilibrium. But the metal feels noticeably colder. Why? Because the metal, with its free electrons, conducts heat away from your warm skin far more rapidly than wood does. Wood relies solely on slow lattice vibrations to move energy. Metal uses both lattice vibrations and fast-moving free electrons. The metal draws energy out of your skin much more quickly, creating a stronger sensation of cold, even though the starting temperature is identical. Your sensation of cold or warmth doesn't measure the temperature of the object directly. It measures the rate at which energy flows into or out of your skin. The faster energy drains from your fingers, the colder the object feels. The metal isn't actually colder than the wood, it's just a more efficient thief of your body's thermal energy. Now let's consider what happens in fluids, in liquids and gases, where atoms and molecules are not locked in a lattice, but are free to move from place to place. Fluids have an additional mechanism for transferring thermal energy that solids lack entirely. It's called convection, and it involves the bulk physical movement of material from one location to another. When you heat water in a pot on a stove, the water at the bottom, in direct contact with the hot metal, absorbs energy and its molecules speed up. As these molecules move faster, they push their neighbours apart slightly, causing the water near the bottom to become less dense than the cooler water above. Less dense fluid rises because it's buoyant. Gravity pulls the denser, cooler water downward, and the warmer, less dense water floats upward. This creates a circulation pattern, a convection current, where warm water rises, cools as it reaches the surface, and gives up energy to the surrounding air, becomes denser again, and sinks back down to be reheated. Round and round, a continuous loop carrying energy from the hot bottom to the cooler surface. Convection is enormously more efficient than conduction alone. Instead of waiting for energy to hop from one molecule to the next through individual collisions, which is slow in a fluid because molecules in a liquid aren't as rigidly coupled as atoms in a solid lattice, convection carries energy by physically transporting the hot material itself to a new location. It's the difference between passing a message down a long line of people one by one and having a messenger run from one end to the other, carrying the message directly. The messenger is faster because the messenger covers the entire distance, not just one link in a chain. Convection shapes the world around you in ways you might not realize. It drives weather patterns in the atmosphere. The sun heats the ground unevenly, and the heated air rises, creating wind and pressure differences that produce everything from gentle breezes to violent storms. Convection drives ocean currents that move enormous quantities of thermal energy around the globe, fundamentally shaping climate. The Gulf Stream, for instance, carries warm water from the tropics northward across the Atlantic, which is why Western Europe has a much milder climate than other regions at the same latitude. Convection also operates inside the Earth itself. The mantle, the thick layer of rock between the crust and the core, convects very slowly over millions of years. Hot rock rises from deep within the Earth, spreads laterally beneath the surface, cools, and sinks back down. This convection drives plate tectonics, moving continents across the globe, opening and closing ocean basins, building mountain ranges, and generating earthquakes and volcanic eruptions. All of it powered by thermal energy flowing through convection from the Earth's hot interior toward its cooler surface. In a gas, molecules fly freely between collisions. In the air around you right now, nitrogen and oxygen molecules are traveling at average speeds of around 500 meters per second. That's faster than a rifle bullet. These molecules collide with each other roughly 10 billion times per second. Each collision redistributes energy. A fast molecule striking a slower one tends to transfer some kinetic energy to the slower particle while itself slowing down. Over countless collisions, the energy distributes statistically across the population of molecules. But the distribution is not uniform. Not every molecule moves at the same speed. Maxwell worked out the precise mathematical distribution of molecular speeds in a gas in the 1860s. What he found is elegant and surprising. At any given temperature, a gas contains molecules traveling at a wide range of speeds. Some molecules are barely creeping along. Others are racing at many times the average speed. Most are somewhere in the middle. The distribution follows a specific mathematical curve, now called the Maxwell-Boltzmann distribution. The shape of this curve depends on temperature and on the mass of the molecules. At a higher temperature, the peak of the distribution shifts to higher speeds and the curve broadens. More molecules are traveling at extreme speeds, both very fast and moderately fast. At a lower temperature, the peak shifts to lower speeds and the distribution narrows. the molecules are more clustered around the average. But at any temperature, there's always a spread. There's always a range of speeds. No matter how cold a gas gets, some molecules will be moving faster than others. The randomness of collisions guarantees this. Energy is constantly being redistributed among molecules through their ceaseless interactions, and the result is a characteristic statistical distribution rather than a single uniform speed. This connects to something profound about the nature of thermal energy and the concept of thermal equilibrium. When two objects are in thermal equilibrium, when they're at the same temperature and no net energy flows between them, it doesn't mean nothing is happening at the microscopic level. Far from it. At equilibrium, energy is still being exchanged between individual particles constantly. Fast molecules are still colliding with slow ones. Energy is still being transferred back and forth across every interface. The difference is that the transfers balance out statistically. For every collision that sends energy from object A to object B, there's, on average, another collision sending the same amount of energy back from B to A. The net flow is zero, but the microscopic activity is furious. Thermal equilibrium is not stillness. It's balanced chaos, a dynamic steady state where energy flows in every direction simultaneously, but cancels out on average. This matters because it reveals that the calm surface of thermal equilibrium conceals an ocean of ceaseless microscopic activity. A room at uniform temperature seems static. Nothing appears to be happening thermally. But if you could zoom in and watch individual molecules, you'd see utter pandemonium. Trillions of particles colliding, exchanging energy, speeding up, slowing down, vibrating, rotating, all in a continuous, furious, random dance. The stillness you perceive at the macroscopic level is an illusion created by statistical averaging over incomprehensibly large numbers of individually chaotic events. This perspective changes how you understand something as simple as a glass of water sitting on a table at room temperature. That glass of water seems perfectly calm, perfectly still, nothing happening. But at the molecular level, the water molecules are crashing into each other billions of times per second. Each molecule is tumbling, vibrating, translating at hundreds of meters per second, ricocheting off its neighbors, exchanging energy with every collision. The molecules at the surface of the water are occasionally moving fast enough to break free entirely, escaping into the air above. That's evaporation, and it happens even when water is well below its boiling point. The fastest molecules in the Maxwell-Boltzmann distribution have enough kinetic energy to overcome the attractive forces holding them in the liquid and launch themselves into the gas phase. Meanwhile, some molecules from the air are striking the water surface and being captured. At equilibrium, the rates of escape and capture balance, but the activity never stops. The surface is a churning battleground of molecular exchange, masked by the calm appearance of a still glass of water. Let's talk about how this microscopic picture connects to the macroscopic measurements we make with thermometers and calorimeters. Because one of the most remarkable achievements of thermal physics is that it bridges these two worlds so precisely. A thermometer works by reaching thermal equilibrium with whatever it's measuring. When you stick a mercury thermometer under your tongue, the mercury absorbs energy from your body until the mercury and your mouth tissues are at the same temperature. At that point, the mercury's volume, which depends on the average kinetic energy of its atoms, stabilizes at a particular reading. The reading tells you the average kinetic energy of the molecules in the thing being measured. It's a macroscopic measurement, a column of liquid at a certain height, that directly reflects a microscopic quantity, the average energy per molecule. But the thermometer cannot tell you about individual molecules. It cannot reveal that some water molecules in your mouth are moving 3 times faster than the average, while others are nearly stationary. It averages everything out. This averaging is both the power and the limitation of macroscopic thermal physics. It lets you make precise, reproducible measurements with simple instruments. But it hides the incredible diversity and complexity of what's really happening at the molecular level. And here's where we encounter the deepest puzzle that classical physics left unresolved. The puzzle that would shatter the foundations of 19th century physics and give birth to an entirely new understanding of nature. Remember the degrees of freedom we discussed? A diatomic molecule like nitrogen should have 7 degrees of freedom in total: 3 translational, 2 rotational, and 2 vibrational. The equipartition theorem says energy should distribute equally among all of them. If that were true, the specific heat of nitrogen gas should reflect all 7 degrees of freedom contributing their share. But when scientists measured the specific heat of nitrogen and other diatomic gases at room temperature, they found that only 5 degrees of freedom were active. The 3 translational and 2 rotational modes were absorbing energy exactly as predicted. But the 2 vibrational degrees of freedom appeared to be completely inactive. The molecules simply weren't storing energy in their vibrational modes at room temperature. The vibrations were frozen out as if they didn't exist. This was baffling. Classical physics offered no explanation whatsoever. In classical mechanics, all degrees of freedom are created equal. There's no reason some should be active while others are dormant. Energy should flow into all available channels without preference or restriction. Yet the experiments were unambiguous. Vibrational modes were silent at room temperature. Only at much higher temperatures, thousands of degrees, did the vibrational modes finally activate and start contributing to the specific heat. Even more troubling was the behavior of solids at low temperatures. The Dulong and Petit law, which correctly predicted the heat capacity of solids at room temperature based on 6 degrees of freedom per atom, broke down badly at low temperatures. As materials were cooled, their heat capacity didn't stay constant. It dropped, eventually plunging towards zero as the temperature approached absolute zero. Degrees of freedom were shutting off one by one as the temperature decreased, as though each mode required a minimum threshold of energy to activate, and temperatures below that threshold couldn't supply it. Classical physics had no mechanism for such thresholds. Energy was supposed to be continuous. You could add any amount, no matter how small, to any degree of freedom. There was no minimum, there was no entry fee. Energy flowed freely and smoothly into every available channel at every temperature. The experimental reality contradicted this fundamental assumption flatly. Something was deeply, structurally wrong with the classical understanding of how energy works at the microscopic level. The failure wasn't subtle. It wasn't a small discrepancy or a minor correction. It was a glaring, systematic, undeniable breakdown of classical theory. The specific heat anomalies, the frozen degrees of freedom, the temperature-dependent behavior that no classical model could reproduce, these problems pointed unmistakably towards something missing from the foundations of physics. Energy at the microscopic scale did not behave the way classical mechanics demanded. It was not continuous. It was not infinitely divisible. It did not flow smoothly and without restriction into every available channel. Something else was going on. Something radical. Something that would require abandoning assumptions that had stood unchallenged for 2 centuries. The answer, when it came, would reshape our understanding not just of heat, but of all physical reality. It came in the form of an idea so strange and so counterintuitive that even the man who proposed it struggled to accept its implications. The idea that energy comes in discrete, indivisible packets, that nature does not allow energy in arbitrary amounts, that there is a minimum quantity, a quantum of energy, below which the universe simply refuses to go. That idea didn't just solve the heat capacity puzzle, it launched an entirely new era in physics. And it's in that quantum world that the true nature of heat finally reveals itself, not as a smooth, continuous flow of shared motion, but as particles jumping between specific, discrete, allowed energy states in a dance governed by the deepest rules nature possesses. By the end of the 1800s, physics was in trouble. Not the kind of trouble where a minor detail needs correcting, the kind of trouble where a foundational pillar of the entire discipline is cracking under the weight of experimental evidence that flatly contradicts it. And the crack appeared in one of the most basic, most familiar physical phenomena imaginable: the glow of a hot object. You've seen it countless times. Heat a piece of metal and it begins to glow. First a dull, barely visible red, then a brighter red, then orange, then yellow, then, at extreme temperatures, a brilliant blue-white. Every object that's hot enough emits visible light, and the color of that light changes with temperature in a very specific, very predictable way. This is thermal radiation, the light that hot objects produce simply because they're hot. And by the late 1800s, physicists had carefully measured the exact spectrum of this radiation across a wide range of temperatures. They knew precisely how much energy was emitted at each wavelength for any given temperature. The measurements were clean, consistent, and reproducible. The problem was that classical physics could not explain them. Physicists had developed a theoretical model for thermal radiation based entirely on established classical principles. Lord Rayleigh and James Jeans applied the equipartition theorem, the same principle that worked so well for gas molecules and their degrees of freedom, to the electromagnetic waves bouncing around inside a perfectly absorbing cavity. The logic was rigorous. An enclosed cavity at a given temperature contains electromagnetic radiation in the form of standing waves. Each standing wave is a mode of vibration, and each mode is a degree of freedom. The equipartition theorem says each degree of freedom should carry the same average energy at thermal equilibrium. At long wavelengths, the prediction matched experiment beautifully. The theory correctly predicted how much energy was radiated in the infrared and at radio wavelengths. But as you move toward shorter wavelengths, toward the ultraviolet end of the spectrum, the prediction went catastrophically wrong. The equipartition theorem predicted that the amount of energy radiated should keep increasing as the wavelength got shorter. Not just increasing a little, increasing without limit. According to the classical calculation, a hot object should radiate infinite energy at short wavelengths. It should emit an unlimited flood of ultraviolet radiation, then X-rays, then gamma rays, in an unending torrent of ever more energetic radiation. This is obviously absurd. Hot objects don't emit infinite energy. If they did, everything warm would instantly incinerate everything around it. You wouldn't be able to light a candle without unleashing a deadly blast of gamma rays. The classical prediction was not merely wrong, it was infinitely wrong. The result was so extreme, so clearly divorced from physical reality, that physicists gave it a dramatic name: the ultraviolet catastrophe. The ultraviolet catastrophe was not a minor failure. It struck at the very heart of classical physics. The equipartition theorem was one of the most well-established results in statistical mechanics. It worked flawlessly for gas molecules. It explained the heat capacity of solids at room temperature. It was a direct mathematical consequence of the assumption that energy is continuous, that you can divide energy into arbitrarily small pieces and distribute it smoothly among all available degrees of freedom. If this assumption led to infinite radiation predictions, something about the assumption itself had to be wrong. In 1900, a German physicist named Max Planck proposed a solution, and his solution was unlike anything physics had seen before. Planck did not tinker with the edges of existing theory. He did not adjust a parameter or add a correction term. He changed the rules at the deepest level. He proposed that energy is not continuous. Instead, energy can only be emitted or absorbed in specific, discrete, indivisible amounts. He called these amounts quanta. Each quantum of energy has a size that depends on the frequency of the radiation. Higher frequency radiation, shorter wavelengths, requires larger quanta. Lower frequency radiation, longer wavelengths, has smaller quanta. The mathematical relationship Planck proposed was strikingly simple. the energy of a single quantum equals a constant, now called Planck's constant, multiplied by the frequency of the radiation. The constant is extremely small, about 6.63 times 10 to the negative 34 joule seconds. This number is so tiny that at everyday scales, the graininess of energy is completely invisible. It would be like saying the ocean is made of individual water molecules. Technically true, but at the scale of waves and tides, the discreteness is utterly irrelevant. You'd never notice it. But at the microscopic level, at the scale of atoms and radiation, Planck's constant is everything. It means that the electromagnetic modes inside a hot cavity cannot absorb energy in arbitrary amounts. Each mode can only absorb energy in lumps of a specific minimum size determined by the mode's frequency. For low-frequency modes with long wavelengths, the quanta are tiny. These modes can easily absorb their share of thermal energy, because even at moderate temperatures, the available thermal energy is more than enough to provide many small quanta. The equipartition theorem works fine for these modes. But for high-frequency modes with short wavelengths, the quanta are large, much larger than the average thermal energy available per mode. These modes require a substantial minimum investment of energy to activate. If the temperature isn't high enough to provide that minimum, the mode stays silent. It absorbs no energy at all. It sits dormant, frozen out, unable to participate in the thermal distribution because the universe refuses to provide a fraction of a quantum. You either get a whole quantum or you get nothing. There is no half measure. There is no partial activation. This single insight, this one radical departure from classical thinking, solved the ultraviolet catastrophe completely. High-frequency modes, the ones that classical theory predicted should carry infinite energy, are suppressed because their quanta are too large to be supplied at any reasonable temperature. The radiation spectrum peaks at a specific wavelength determined by the temperature, and then falls off sharply at shorter wavelengths, exactly as experiments showed. Planck's quantum hypothesis reproduced the measured spectrum of thermal radiation with perfect precision. Every detail matched. The mathematical formula he derived, now called Planck's law of black body radiation, remains one of the most precisely verified equations in all of physics. But Planck himself was deeply uncomfortable with what he had done. He considered the quantization of energy a mathematical trick, a calculation device that produced the right answer without necessarily reflecting physical reality. He spent years trying to derive the same result using classical methods. He never succeeded. The quantization was not a trick. It was a window into the deepest structure of nature. Energy truly comes in discrete packets. This is not an approximation or a simplification. It is how the universe actually works. The next breakthrough came from Albert Einstein. In 1907, Einstein applied Planck's quantum idea directly to the puzzle that had defeated classical physics for decades: the mysterious drop in the heat capacity of solids at low temperatures. Remember the problem. Classical theory, through the equipartition theorem, predicted that every atom in a solid should have 6 degrees of freedom, all active at every temperature. This gave a constant heat capacity matching the Dulong and Petit law. But experiments showed that heat capacity dropped dramatically at low temperatures, approaching zero as the material approached absolute zero. Classical physics could not explain this. Einstein proposed a beautifully simple model. He treated each atom in a solid as an independent quantum oscillator, vibrating in 3 dimensions around its lattice position. Crucially, these oscillators were quantum oscillators, not classical ones. A classical oscillator can vibrate with any amplitude and carry any amount of energy, no matter how small. A quantum oscillator cannot. It can only exist in specific, discrete energy states. The lowest energy state is the ground state. Above that is the first excited state, carrying exactly 1 quantum of vibrational energy. Above that is the second excited state, carrying exactly 2 quanta, and so on. The gap between adjacent energy levels is always the same for a given oscillator, and its size depends on the oscillator's natural frequency multiplied by Planck's constant. At high temperatures, when there's plenty of thermal energy available, each oscillator can easily absorb many quanta and populate high energy levels. All 6 degrees of freedom are effectively active. The heat capacity matches the classical prediction. Everything looks normal. But as the temperature drops, the average thermal energy available to each oscillator decreases. At some point, the thermal energy becomes comparable to the quantum energy gap. Below this temperature, many oscillators simply cannot absorb even a single quantum of vibrational energy because the thermal energy available isn't enough to bridge the gap between the ground state and the first excited state. These oscillators remain stuck in their ground states, unable to store additional thermal energy, unable to contribute to the heat capacity. This is exactly what the experiments showed. At low temperatures, degrees of freedom freeze out one by one because the thermal energy drops below the minimum quantum required to activate them. Einstein's model reproduced the overall shape of the heat capacity curve beautifully. It showed a smooth transition from the full classical value at high temperatures to near zero at low temperatures, matching the experimental trend. Einstein's model wasn't quite perfect in its details. It assumed all atoms vibrate at the same frequency, which is an oversimplification. In a real solid, atoms are coupled to their neighbors through bonds, and the vibrations propagate through the entire lattice as waves. Different wave patterns have different frequencies, and a realistic model needs to account for this entire spectrum of vibrational frequencies. In 1912, the Dutch physicist Peter Debye produced a more refined model that treated the vibrations of a solid lattice as a spectrum of waves with a range of frequencies from low to high, rather than assuming a single frequency. Debye's model matched experimental heat capacity data with remarkable precision across the full range of temperatures, from near absolute zero to well above room temperature. The low temperature behavior followed a specific mathematical law, heat capacity proportional to the cube of the temperature, that Debye predicted and experiments confirmed exactly. This was a triumph of quantum theory applied to thermal physics. But the quantum revolution went deeper still. Not only is the energy of individual oscillators quantized, the vibrations themselves come in discrete packets. These quantized vibrations of a crystal lattice have a name. They're called phonons. And understanding phonons is essential to understanding what heat is at the quantum level in solid materials. A phonon is to a lattice vibration what a photon is to a light wave. Just as light, which classically appears as a smooth electromagnetic wave, is actually composed of discrete energy packets called photons, the vibrations traveling through a crystal lattice, which classically appear as smooth, sound-like waves, are actually composed of discrete energy packets called phonons. Each phonon carries a specific quantized amount of vibrational energy. You cannot have half a phonon. You either have one or you don't. The lattice vibrations are not continuous waves that can carry any amount of energy. They're streams of individual phonons, each one an indivisible quantum of vibrational energy. When you heat a solid, you are creating phonons. The thermal energy you add doesn't smoothly increase the amplitude of lattice vibrations in a continuous way. Instead, it creates more phonons. At higher temperatures, there are more phonons bouncing around inside the lattice, each carrying its own quantum of vibrational energy. At lower temperatures, there are fewer phonons. At absolute zero, in the classical picture, there would be no phonons at all. Though, as we'll discuss later, quantum mechanics has something surprising to say about even that seemingly simple statement. Thermal conduction in a solid, the process by which energy moves from one end of a metal rod to the other, is actually the transport of phonons. When the hot end of a rod vibrates violently, those vibrations propagate through the lattice as phonons traveling from the hot region toward the cold region. The phonons carry energy with them as they move. When they reach the cooler region, they interact with the less energetic lattice atoms there, transferring their energy and warming that part of the material. Phonons can scatter off impurities in the lattice, off grain boundaries in polycrystalline materials, and off each other. These scattering events determine how efficiently a material conducts heat. A material with few impurities and a highly ordered crystal structure allows phonons to travel long distances without scattering, making it a good thermal conductor. A disordered or impure material scatters phonons frequently, impeding their flow and making the material a poor conductor.
So heat conduction in a solid is not just atoms pushing their neighbours in a chain of classical collisions. It is the flow of quantum particles, phonons, through a crystalline medium. The energy travels as discrete quantized packets of vibration, not as smooth continuous waves. This is a fundamentally quantum picture of thermal energy transport. Now, to fully understand how thermal energy distributes itself among quantum states, you need to understand quantum statistics. Because at the quantum level, particles don't follow the same statistical rules as classical objects. They follow different rules depending on what type of particle they are. And these different rules have profound consequences for thermal physics. In classical statistical mechanics, developed by Boltzmann in the 1870s, every particle is distinguishable. Each molecule has its own unique identity. You can, in principle, label them and track them individually, and every arrangement of particles among available energy states is equally probable. This works perfectly well for everyday gases and liquids at moderate temperatures where quantum effects are negligible. But at the quantum level, particles are fundamentally indistinguishable. Two electrons are not merely similar, they are identical in the deepest possible sense. You cannot paint one red and the other blue. You cannot attach labels to them. There is no experiment you can perform, even in principle, that would tell two electrons apart. Swapping two identical quantum particles produces a state that is physically indistinguishable from the original. This indistinguishability changes the statistics entirely. And nature provides two distinct sets of quantum statistical rules for two fundamentally different classes of particles. The first class is called bosons, and phonons and photons both belong to this class. Bosons follow a set of statistical rules worked out by Satyendra Nath Bose and Albert Einstein in 1924 and 1925. The rules are called Bose-Einstein statistics. The defining feature of bosons is that any number of them can occupy the same quantum state simultaneously. There's no limit. You can pack as many photons or phonons into a single energy level as you like. They're sociable particles in a sense. They're happy to crowd together. This has enormous consequences for thermal physics. At low temperatures, bosons tend to cluster into the lowest available energy states. Many bosons can pile into the ground state simultaneously because there's no exclusion rule preventing it. This clustering affects how energy distributes across quantum states and changes the thermal properties of systems made of bosons. The thermal radiation inside a hot cavity, for instance, consists of photons, which are bosons. The spectrum of that radiation, Planck's law, is derived directly from Bose-Einstein statistics applied to a gas of photons in thermal equilibrium. The entire shape of the thermal radiation spectrum, the peak wavelength, the total radiated power, everything follows from the quantum statistics of bosons. Similarly, phonons in a solid are bosons. The thermal energy stored in a crystal lattice, the number and distribution of phonons across different vibrational modes, follows Bose-Einstein statistics. Debay's successful model of heat capacity is built on this foundation. The reason heat capacity drops at low temperatures is that quantum statistics prevents the high-frequency vibrational modes from being populated when the temperature is too low to supply their minimum quantum of energy. The Bose-Einstein distribution function tells you precisely how many phonons occupy each mode at each temperature, and from that, you can calculate the total thermal energy and the heat capacity with extraordinary precision. The second class of particles is called fermions. Electrons belong to this class, along with protons, neutrons, and quarks.
Fermions follow a completely different set of statistical rules worked out by Enrico Fermi and Paul Dirac in 1926. These rules are called Fermi-Dirac statistics. The defining feature of fermions is the exact opposite of bosons. No two fermions can occupy the same quantum state simultaneously. This is called the Pauli exclusion principle, and it's one of the most important rules in all of quantum physics. The exclusion principle means that fermions must stack up into successively higher energy levels. The lowest level can hold a limited number of fermions. Once it's full, the next fermion must go into the next level up, and the next into the level above that. In a metal at absolute zero, the free electrons fill energy levels from the bottom up, one after another, like stacking balls into shelves. The highest occupied energy level at absolute zero is called the Fermi energy. This has a remarkable implication for thermal energy in metals. Remember that metals contain free electrons that carry thermal energy and contribute to thermal conduction. You might expect that when you heat a metal, all the free electrons should speed up, absorbing thermal energy and contributing to the heat capacity. But that's not what happens. Because of the Pauli exclusion principle, most of the electrons are trapped deep inside completely filled energy levels. They cannot absorb a small amount of thermal energy because the nearby energy levels are already occupied. They're stuck. The only electrons that can absorb thermal energy are the ones near the top of the filled levels, near the Fermi energy, where there are empty states available just above them. At room temperature, only a tiny fraction of the free electrons in a metal, roughly 1% or less, can actually participate in thermal processes. The rest are locked in place by the exclusion principle, unable to gain or lose energy. This is why the electronic contribution to the heat capacity of metals is much smaller than classical theory predicted. Classical theory assumed all free electrons could absorb energy. Quantum statistics reveals that almost none of them can. Only the thin layer of electrons near the Fermi surface contributes to thermal properties. This was a puzzle that classical physics could not explain, and that Fermi-Dirac statistics resolved completely. So at the quantum level, what does heat transfer actually look like? It looks like particles transitioning between allowed quantum states. When a hot object transfers energy to a cold one, what's happening microscopically is that particles in the hot object are making quantum transitions from higher energy states to lower ones, and particles in the cold object are making transitions from lower states to higher ones. The energy released by downward transitions in the hot object is absorbed by upward transitions in the cold object. Each transition involves a specific quantized amount of energy. The energy doesn't flow smoothly or continuously. It moves in discrete jumps as individual particles hop between allowed quantum levels. In a solid, this means phonons are being created in the hot region and absorbed in the cold region. The flow of thermal energy is literally a flow of quantum particles. In a gas, molecules transitioning between rotational and vibrational quantum states exchange energy through collisions. A fast molecule colliding with a slow one can cause the slow molecule to jump to a higher rotational state, absorbing a quantum of rotational energy and slowing the fast molecule by exactly that amount. The energy exchange is quantized. It comes in specific lumps determined by the spacing of the quantum energy levels. This quantized picture of heat transfer is fundamentally different from the classical view of smooth, continuous energy sharing through collisions. Classical physics imagined energy flowing like water, continuously and in any amount.
Quantum physics reveals that energy moves like a currency with a smallest denomination. You can transfer 1 quantum, or 2 quanta, or 100 quanta, but you cannot transfer a fraction of a quantum. The exchange is always discrete, always exact, always governed by the specific energy level structure of the particles involved. The quantum energy level structure also explains why different substances absorb heat differently at different temperatures. Each material has its own unique set of quantum energy levels, determined by its atomic composition, its bonding, and its crystal structure. The spacing between these levels determines how easily the material can absorb thermal energy at a given temperature. If the level spacing is small compared to the available thermal energy, the material absorbs energy readily and has a high heat capacity. If the level spacing is large, the material requires more energy to excite transitions, and its heat capacity is lower. This is why vibrational degrees of freedom in diatomic gases are frozen out at room temperature, but become active at high temperatures. The quantum energy levels for molecular vibration are widely spaced because vibrational frequencies are high. At room temperature, the thermal energy available is simply not enough to promote molecules from the ground vibrational state to the first excited vibrational state. The gap is too large. So the vibrational modes sit dormant, contributing nothing to the heat capacity. But rotational energy levels are much more closely spaced because rotational frequencies are lower. Even at room temperature, there's more than enough thermal energy to populate many rotational states. So rotational modes are active and contribute their full share to the heat capacity. As you raise the temperature, more thermal energy becomes available. At some point, the thermal energy becomes comparable to the vibrational energy gap, and molecules begin making vibrational transitions. The vibrational modes activate. The heat capacity increases. This threshold behavior, modes switching on as temperature rises and switching off as temperature falls, is entirely a quantum effect. It has no classical explanation. Classical physics says all modes should be active at all temperatures. Quantum physics says modes activate only when the temperature is high enough to supply the minimum quantum of energy they require. The same principle applies to atoms in a solid lattice. At low temperatures, the high-frequency vibrational modes require large quanta that the meager thermal energy cannot supply. These modes are frozen out and contribute nothing to the heat capacity. As the temperature rises, progressively higher frequency modes become accessible, each activating as the thermal energy crosses its quantum threshold. The heat capacity rises smoothly from near zero at very low temperatures to the full classical value at high temperatures, exactly as Debye's model predicts and experiments confirm. This is the quantum picture of thermal energy in matter. Energy is stored in the quantum states of particles. It occupies specific discrete levels within atoms, molecules, and crystal lattices. It is exchanged through quantum transitions, through phonon creation and absorption, through photon emission and absorption, through molecular collisions that promote or demote particles between quantized rotational and vibrational states. The thermal energy of a substance is not a smooth, continuous distribution of kinetic energy across infinitely divisible degrees of freedom. It is a collection of quantum excitations, each one discrete, each one governed by the rules of quantum mechanics, each one carrying a specific, quantized packet of energy. And the statistical distribution of these excitations across available quantum states follows quantum statistics. Bosons follow Bose-Einstein statistics, clustering together in low energy states at low temperatures.
distributing broadly across many states at high temperatures. Fermions follow Fermi-Dirac statistics, stacking into successively higher energy levels, with only those near the top of the stack able to participate in thermal processes. Temperature, in this quantum framework, takes on a precise and beautiful meaning. Temperature measures how broadly thermal excitations are distributed across quantum states. At low temperature, excitations are concentrated in the lowest energy levels. Only a few states are occupied. The system is ordered and predictable. At high temperature, excitations spread broadly across many energy levels. Many states are occupied. The system is disordered and chaotic. Temperature is the parameter that controls this spread, that determines the statistical probability of finding a given quantum state occupied. Heat, then, is the energy that flows between two systems because their quantum excitations are distributed differently. When a hot system touches a cold system, the hot system has excitations spread broadly across high-energy quantum states, while the cold system has excitations concentrated in low-energy states. Through interactions, collisions, and quantum transitions, excitations redistribute themselves. High-energy excitations in the hot system decay, releasing quanta of energy. Low-energy states in the cold system absorb those quanta, promoting particles to higher levels. The process continues until both systems have the same statistical distribution of excitations, until they reach the same temperature, at which point net energy transfer stops and thermal equilibrium is established. This is what heat is made of at the quantum level. Not a fluid, not simply molecules moving. It is the transfer of quantized energy between systems through the redistribution of quantum excitations across discrete energy states. It is phonons flowing through crystal lattices. It is molecules jumping between rotational and vibrational quantum levels through collisions. It is photons being emitted by excited atoms and absorbed by unexcited ones. It is electrons near the Fermi surface gaining and losing tiny amounts of kinetic energy as the exclusion principle allows. All of these processes are quantum. All of them involve discrete energy packets. All of them are governed by quantum statistics, and together they constitute what we experience as heat. The quantum revolution didn't replace the kinetic theory of heat. It deepened it. It revealed the hidden structure beneath the classical picture. Atoms and molecules are indeed in constant motion, and that motion does carry thermal energy. But the motion is quantized. The energies are discrete. The statistics are fundamentally different from anything classical physics imagined. And there remains one more piece of the puzzle that we haven't yet explored. The way thermal energy can travel across empty space, carrying heat between objects separated by millions of miles of vacuum, without any atoms or molecules to serve as intermediaries. That mechanism is thermal radiation, energy carried by photons, and it reveals perhaps the most elegant connection between quantum mechanics and the everyday experience of warmth. There is one more way that heat travels through the universe, and it's the most remarkable of all, because this method requires no atoms, no molecules, no physical material of any kind between the source and the destination. It works across the cold, airless vacuum of space, bridging distances of millions or even billions of miles with nothing but light. This is thermal radiation, and every object in the universe that has a temperature above absolute zero produces it. Right now, as you listen to this, your body is radiating energy. The walls of the room you're sitting in are radiating energy. The chair beneath you, the floor under your feet, the screen in front of you. All of them are constantly, silently, ceaselessly emitting electromagnetic radiation, simply because they have a temperature. You can't see most of this radiation because it's in the infrared range, below the threshold of human vision. But it's there. It never stops. Every object is a source of thermal radiation, and every object is simultaneously absorbing thermal radiation from everything around it. You've actually experienced this directly, even if you didn't realize what was happening. When you stand near a campfire, you feel warmth pressing against your face, even though you're not touching the flames, and the air between you and the fire might even feel cool. That warmth isn't coming from hot air convecting toward you, at least not primarily. It's coming from infrared photons emitted by the flames and the glowing coals, traveling through the air at the speed of light and being absorbed by your skin. Each photon deposits its tiny quantum of energy into the molecules of your skin, causing them to vibrate faster. Your nerve endings detect this increase in molecular motion and interpret it as warmth. You are being heated by light, by individual packets of electromagnetic energy crossing the gap between the fire and your face. This is how the sun heats the Earth. Think about that for a moment. The sun is roughly 93 million miles away from our planet. Between the sun and the Earth is essentially nothing, hard vacuum. No air, no gas, no material of any kind to conduct or convect energy from one place to the other. And yet, the sun's energy reaches us. It warms our planet. It powers the climate. It drives photosynthesis. It sustains virtually all life on Earth. All of that energy crosses 93 million miles of empty space, carried by nothing more than photons. Quantum packets of electromagnetic radiation, each one traveling at 300,000 kilometers per second, each one carrying a specific quantized amount of energy determined by its frequency. Roughly 8 minutes and 20 seconds after a photon leaves the surface of the sun, it strikes the Earth's atmosphere or surface. When it's absorbed by a molecule in the air or by an atom on the ground, it ceases to exist as a photon, and its energy becomes thermal energy in the absorbing material. The molecule vibrates faster, the atom moves more quickly, the material warms up. Thermal radiation has been converted into the microscopic motion of matter. A photon born in the nuclear furnace at the sun's core, after spending perhaps 100,000 years bouncing through the sun's dense interior, finally escaped from the surface, travelled across the vacuum of space for 8 minutes, and delivered its quantum of energy to a patch of ground, or a leaf, or the surface of an ocean on a small rocky planet. That quantum of energy is now thermal energy in the Earth system. It is heat, transferred across empty space by a quantum of light. The spectrum of thermal radiation, the distribution of energy across different wavelengths, follows a precise mathematical law. Max Planck derived this law in 1900, and it bears his name. Planck's law tells you exactly how much energy is radiated at each wavelength by an object at a given temperature. The spectrum has a characteristic shape. It rises from zero at very short wavelengths, peaks at a specific wavelength that depends on the temperature, and then falls off gradually at longer wavelengths. The hotter the object, the shorter the peak wavelength. This is why a glowing piece of metal changes color as it heats up. At lower temperatures, the peak is in the infrared, invisible to human eyes. As the temperature increases, the peak shifts into the visible spectrum. First deep red, then orange, then yellow, then blue-white at extreme temperatures. The color of the glow tells you the temperature because the peak wavelength is directly and precisely related to how hot the object is. This relationship was discovered experimentally by Wilhelm Wien in 1893 and is now called Wien's displacement law.
The peak wavelength is inversely proportional to the temperature. Double the temperature, and the peak wavelength is cut in half. The Sun, with a surface temperature of about 5,500 degrees Celsius, peaks in the visible part of the spectrum, which is no coincidence. Human eyes evolved to be most sensitive to the wavelengths where our star emits the most energy. We see the universe through a window that the Sun's temperature opened for us. The total amount of energy radiated by a hot object increases enormously with temperature. This was quantified even earlier by Joseph Stephan in 1879 through experiment, and later derived theoretically by Ludwig Boltzmann. The total radiated power is proportional to the fourth power of the absolute temperature. If you double an object's absolute temperature, it radiates not twice as much energy, but 16 times as much. Triple the temperature, and the radiation increases 81-fold. This steep dependence on temperature means that hot objects radiate vastly more energy than cool ones. The Sun, at roughly 5,800 Kelvin, radiates an incomprehensibly greater amount of energy per square meter of surface than the Earth, at roughly 288 Kelvin. Even though both objects emit thermal radiation continuously, the intensities differ by a factor of millions. Now, every photon emitted as thermal radiation is a quantum particle. It carries a discrete packet of energy equal to Planck's constant multiplied by the photon's frequency. Higher frequency photons carry more energy per quantum. Lower frequency photons carry less. The thermal radiation from a hot object is a stream of photons with a specific statistical distribution of energies determined by the object's temperature and governed by Bose-Einstein statistics, because photons are bosons. At thermal equilibrium, an object absorbs exactly as much radiation as it emits. The incoming and outgoing streams of photons carry equal total energy. The object's temperature stays constant. But if an object is hotter than its surroundings, it emits more thermal radiation than it absorbs, and it cools down. If it's cooler than its surroundings, it absorbs more than it emits, and it warms up. This is how thermal equilibrium is maintained through radiation. It's the same principle as conduction and convection, energy flowing from hot to cold, but the mechanism is entirely different. No atoms need to be in contact. No material needs to be present between the objects. Photons carry the energy across any distance through any vacuum at the speed of light. This means thermal radiation connects everything in the universe thermally. Every object with a temperature above absolute zero is constantly emitting and absorbing photons. Stars radiate energy into space. Planets absorb some of that energy and radiate their own thermal spectrum back into the void. Even the cold dust between stars emits faint infrared radiation corresponding to its frigid temperature of perhaps 10 or 20 Kelvin. The entire universe is pervaded by a bath of thermal radiation, the cosmic microwave background, left over from roughly 380,000 years after the Big Bang. This radiation has cooled over billions of years of cosmic expansion to a current temperature of about 2.7 Kelvin, just a few degrees above absolute zero. It fills every cubic centimeter of space. It is the thermal radiation of the universe itself, a relic glow from the moment the cosmos first became transparent to light. This brings us to one of the most fascinating questions in all of thermal physics. What happens at the bottom of the temperature scale? What happens as you approach absolute zero? Absolute zero is 0 Kelvin, or roughly negative 273.15 degrees Celsius. It's the lowest possible temperature, the point at which, according to classical physics, all molecular motion should cease entirely. Every atom should stop moving. Every vibration should fall silent. All thermal energy should drain away to nothing, leaving matter perfectly still and perfectly cold. But quantum mechanics tells us something remarkable. You cannot actually reach absolute zero, and even if you could get infinitely close, matter would not be perfectly still. It would retain a minimum, irreducible amount of energy that can never be removed. This residual energy is called zero-point energy. It's a direct consequence of the Heisenberg uncertainty principle, one of the most fundamental rules in quantum mechanics. Werner Heisenberg showed in 1927 that you cannot simultaneously know both the exact position and exact momentum of a particle with perfect precision. There is a fundamental minimum uncertainty that nature imposes. If you know precisely where a particle is, its momentum becomes completely uncertain. If you know its momentum precisely, its position becomes uncertain. You can never pin down both at once. Now consider what this means for an atom vibrating in a crystal lattice. If the atom were perfectly stationary, sitting motionless at its exact equilibrium position, you would know both its position with certainty, right at the lattice site, and its momentum with certainty, exactly zero. But the uncertainty principle forbids this. The atom cannot have both zero momentum and a perfectly defined position simultaneously. Therefore, even at absolute zero, the atom must retain some residual motion. It must still vibrate, however slightly, because perfect stillness would violate a fundamental law of quantum mechanics. This is zero-point energy. It's the energy of the ground state, the lowest possible quantum state of the system. You can never remove it. You can never go below it. It's built into the fabric of quantum mechanics itself. Every quantum oscillator, every vibrating atom in every crystal lattice in the universe possesses this irreducible minimum energy. Even at absolute zero, matter is not still. It hums with a faint, inextinguishable quantum vibration that can never be silenced. Zero-point energy is not just a theoretical curiosity. It has measurable physical consequences. It affects the crystal structure of solid helium. Helium atoms are so light and their interatomic forces so weak that zero-point energy is comparable to the binding energy holding the solid together. This is why helium remains a liquid at atmospheric pressure all the way down to absolute zero. No matter how cold you make it, the zero-point motion of the helium atoms is vigorous enough to prevent them from settling into a rigid crystalline lattice. Helium only solidifies under significant external pressure, which forces the atoms close enough together that the binding forces finally overcome the zero-point motion. No other element behaves this way. Helium's refusal to freeze is a direct, visible, macroscopic consequence of quantum zero-point energy. The third law of thermodynamics formalizes the impossibility of reaching absolute zero. Stated by Walter Nernst around 1905 and refined over the following decade, the third law says that no finite number of steps can bring a system all the way to absolute zero. You can get closer and closer, approaching it asymptotically, but you can never arrive. Each successive step of cooling removes less and less energy because there's less and less to remove. And the final residue, the zero-point energy, cannot be removed at all. Modern laboratories have achieved temperatures extraordinarily close to absolute zero. In 1995, physicists Erich Cornell, Carl Wieman, and Wolfgang Ketteler cooled small clouds of rubidium and sodium atoms to temperatures below 1/1,000,000th of a Kelvin, just hundreds of billionths of a degree above absolute zero. At these astonishingly low temperatures, something extraordinary happens. The atoms undergo a phase transition into a new state of matter called a Bose-Einstein condensate. This phenomenon was predicted theoretically by Einstein in 1925, based on the quantum statistical work of Satyendra Nath Bose, but it took 70 years before experimental technology advanced enough to produce one in a laboratory. In a Bose-Einstein condensate, atoms cooled to near absolute zero all drop into the same quantum ground state simultaneously. They lose their individual identities and behave as a single quantum entity. A collective wave of matter where thousands or millions of atoms occupy exactly the same quantum state, moving in perfect lockstep, behaving not like individual particles, but like one unified quantum object large enough to observe directly. This is only possible because the atoms used in these experiments are bosons. They follow Bose-Einstein statistics, which allows unlimited occupancy of a single quantum state. At sufficiently low temperatures, the atom's thermal energy becomes so small that their quantum wavelengths expand until they overlap. The atoms can no longer be distinguished from one another. They merge into a single macroscopic quantum state. A Bose-Einstein condensate is a dramatic demonstration of quantum thermal physics. It shows what happens when you remove nearly all thermal energy from a system. When you cool matter to the point where almost all quantum excitations have been drained away, you don't get stillness. You get something far stranger. You get quantum behavior made visible at macroscopic scales. The weird, counterintuitive properties of quantum mechanics that normally operate only at the atomic level suddenly manifest in objects large enough to photograph. There's another exotic quantum phenomenon revealed at extremely low temperatures: superconductivity. In 1911, the Dutch physicist Heike Kamerlingh-Onnes discovered that when mercury was cooled below about 4 Kelvin, its electrical resistance vanished completely. Not reduced to a tiny value, completely gone. An electrical current set flowing in a superconducting ring would circulate forever without any loss of energy. This is not merely very low resistance, it is zero resistance, a qualitatively different state from normal conduction. Superconductivity is fundamentally a thermal quantum phenomenon. At low enough temperatures, electrons in certain materials pair up into structures called Cooper pairs. These pairs behave as bosons despite being composed of two fermions, and they condense into a collective quantum ground state analogous to a Bose-Einstein condensate. In this condensed state, the paired electrons flow through the material without scattering, without losing energy, without resistance. Thermal energy is the enemy of superconductivity. Above a certain critical temperature, the thermal vibrations of the lattice are violent enough to break apart the Cooper pairs, destroying the superconducting state and restoring normal electrical resistance. Below that temperature, the quantum ground state is stable and resistance vanishes. These extreme low-temperature phenomena, Bose-Einstein condensates, superconductors, superfluid helium, all represent the quantum nature of thermal energy laid bare. They show what happens when you strip away almost all thermal excitations and expose the quantum ground state beneath. They reveal that matter at its coldest is not inert. It is quantum mechanical. It possesses zero-point energy. It exhibits collective quantum behavior. It obeys Bose-Einstein or Fermi-Dirac statistics, depending on the particles involved. The thermal energy that we experience as warmth, as the familiar sensation of a hot cup between our hands, is in fact a thick blanket of quantum excitations covering a strange, subtle quantum world underneath. Remove the blanket, and the underlying quantum reality emerges. Now let's bring everything together. Let's answer the question we started with as completely and clearly as we can. What is heat made of according to quantum physics? Heat is not a substance. This was the first and most important lesson. For over a century, scientists believed heat was an invisible fluid called caloric that flowed between objects.
Careful experiments by Count Rumford and James Prescott Joule demolished this idea. Heat is not a thing that objects contain. It is not a material you can pour or store or trap. Heat is energy in transit. It exists only in the process of being transferred from one system to another because their temperatures differ. Once the energy has been absorbed by the receiving system and is contributing to its internal energy, it is no longer heat. It is simply energy stored in the microscopic motions and quantum states of that system's particles. Heat is not simply molecules moving. This is an important nuance that many explanations get wrong. The kinetic theory of matter correctly identifies the microscopic basis of thermal energy as the motion of atoms and molecules. But describing heat as just molecules bouncing around misses the essential quantum structure. The motions are quantized. The energies are discrete. The vibrations come in indivisible packets called phonons. The rotations and vibrations of molecules can only take specific allowed values. The statistics governing how energy distributes across these states are quantum statistics, not classical. The classical picture of smoothly sharing energy through billiard ball collisions is an approximation that works at everyday scales, but breaks down fundamentally when you look closely. Heat is energy transferred through quantum degrees of freedom. Every atom and molecule possesses a specific set of quantum states it can occupy. Translational states for the motion of whole molecules through space. Rotational states for molecules tumbling end over end. Vibrational states for atoms oscillating within their bonds or within a crystal lattice. Electronic states for electrons orbiting nuclei or flowing through metals. Each of these modes can absorb and release energy, but only in discrete, quantized amounts. The thermal energy of a substance is the collective energy stored across all these quantum states in all the particles of the material. When energy transfers from a hotter system to a cooler one, particles in the hot system make downward quantum transitions, releasing energy, while particles in the cold system make upward transitions, absorbing it. Heat travels by conduction, the flow of phonons and free electrons through solid materials, passing energy from vibrating atom to vibrating atom through the quantum coupling of their bonds. Heat travels by convection, the bulk physical movement of hot fluid carrying its excited quantum states from one place to another. And heat travels by radiation, photons carrying quantized energy across empty space at the speed of light, requiring no medium and no physical contact, connecting objects separated by any distance. The reason matter feels hot to your touch is that the fast vibrating atoms at its surface transfer kinetic energy to the slower molecules in your skin through microscopic collisions. Each collision involves a quantum exchange of energy. The accumulated effect of billions of these quantum-scale interactions per second is what your nerve endings detect as warmth. There is no heat fluid entering your body. There is no substance flowing into you from the hot object. There is only energy, carried by quantum transitions and microscopic collisions, redistributing itself from a region of higher average energy to a region of lower average energy. The reason matter feels cold isn't because cold is a thing being transferred to you. Cold is the absence of thermal excitations. When you touch something cold, your skin's thermal energy flows out of you into the colder object. Your molecules slow down. You lose quantum excitations, and your nerves interpret that loss as the sensation of cold. Cold is not something you receive, it's something you give away. Temperature measures how broadly quantum excitations are distributed across available energy states. At high temperature, excitations spread across many states, populating high energy levels. At low temperature, excitations concentrate in the lowest states. Absolute zero is the state where the system occupies its quantum ground state and no further energy can be extracted. But even there, zero-point energy remains, a permanent, irreducible quantum vibration that can never be silenced. And the second law of thermodynamics, the fundamental principle that energy flows spontaneously from hot to cold, arises not from any force or mechanism pushing energy in a particular direction. It arises from probability, from the overwhelming statistical likelihood that when trillions of quantum transitions occur simultaneously across countless particles, the net effect is energy flowing from regions with broadly distributed excitations to regions with narrowly distributed excitations. It is not a commandment. It is a mathematical certainty born from the sheer weight of numbers. So the next time you hold a warm cup of coffee in your hands and feel that comforting heat seeping into your fingers, consider what is actually happening. Trillions of atoms in the ceramic are vibrating in quantized modes. Phonons are flowing through the lattice, carrying discrete packets of vibrational energy toward the surface. At the boundary where the cup meets your skin, fast vibrating ceramic atoms collide with slower molecules in your tissue, transferring energy in quantized increments through countless microscopic interactions. Your molecules speed up. Your nerve endings register the change, and you feel warmth. No substance has moved from the cup to your hand. No invisible fluid has flowed between them. What you're feeling is the accumulated macroscopic signature of trillions of quantum transitions happening simultaneously at the atomic scale. Each one discrete, each one governed by quantum mechanics, each one carrying a specific, indivisible packet of energy from one system to another. Heat is not a substance. It is not a simple vibration. It is the transfer of energy through the quantum fabric of matter and light. It is phonons rippling through crystal lattices. It is molecules leaping between quantized rotational and vibrational states. It is photons sailing across the vacuum of space, carrying energy from stars to planets. It is electrons near the Fermi surface, absorbing tiny quanta of kinetic energy in a metal. It is the statistical redistribution of quantum excitations among countless particles, driven by probability, governed by quantum rules, connecting everything in the universe through the ceaseless exchange of energy. That warmth you feel right now, the warmth of being alive, of blood circulating through your body, of metabolic reactions converting chemical energy into thermal energy in every one of your cells. That warmth is a quantum phenomenon. It is the collective hum of trillions upon trillions of quantum transitions sustaining the delicate thermal balance that keeps you alive. The universe runs on heat. Stars generate it through nuclear fusion. Planets absorb it through radiation. Life harnesses it through chemistry. And at every level, from the nuclear furnace of a star's core to the gentle warmth of human skin, heat is the same thing.
Energy transferred between systems through the quantum degrees of freedom of matter and light. Discrete, quantized, beautiful. And now, you understand what it's really made of. Thank you for joining me on this journey into the quantum heart of something we all feel but rarely truly understand. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep explorations of the science that shapes our world. And the next time you feel warmth on your skin, remember, you're feeling quantum mechanics in action. Billions of years of physics, from the birth of stars to the structure of atoms to the strange rules of quantum theory, all of it condensed into that simple, familiar sensation. Good night.